Hello, everyone, and welcome to KITE Research Rounds. It's my pleasure to introduce our speaker, Professor Albert Vette. Dr. Vette is an associate professor in the Department of Mechanical Engineering, University of Alberta, where he's the director of the Neuromuscular Control and Biomechanics Lab. He's also a research scientist at the Glenrose Rehab Hospital in Edmonton and a member of the Neuroscience and Mental Health Institute and SMART Network, both at the University of Alberta. Dr. Vette received his PhD in biomedical engineering at the University of Toronto and completed the MITACS postdoctoral fellowship in human movement sciences at Toronto Rehab and the University of Waterloo. Dr. Vette has published more than 60 peer-reviewed journal articles in the domains of human movement neuromechanics, quantitative performance assessments, and rehabilitation engineering. Using both experimental and theoretical means, his team's efforts are focused on gaining a better understanding of how we control movements and on enhancing functional independence following neuromuscular impairment. Please join me in a virtual round of applause to welcome Dr. Vette.
Yeah, good afternoon, everyone. And thank you so much, Babak, for the introduction and for inviting me. It's a pleasure to be back here at Toronto Rehab virtually, but hopefully someday soon I can come back in person. My time in Toronto back when I was a grad student and postdoc was certainly one of the best times of my life, being mentored by Milos, Kay, but also Bill during my postdoc. Having met my wife there and also 2 kids there, and one came later here in Edmonton. So it's great to be back and hopefully soon in person. And yeah, my ties to Toronto Rehab are still active. I work with Kay, I work with TLAC, and hopefully that will continue into the future. Today, I would like to talk about some of our research here in Edmonton. And the topic of my talk here is emerging neuromuscular techniques for assessing, training, and restoring trunk stability. I thought about it, what I could talk to. I also thought about more focusing on the upper body in terms of the upper limb function, but I thought it may be nice to connect to some of the work that I've done as a graduate student and also postdoc. So with this in mind, I'll get started here. But before I dive into this topic, which hopefully presents some of different things for all of you, so more on the technological side of things, but also more on the theoretical side of things, and then more on the clinical side of things. So hopefully there'll be aspects for everyone. But before I do this, maybe I'll just give a quick introduction to my work here at the University of Alberta. Let me just try to advance the slide here. There we go. Now it works. All right, so my field of work is mostly on the neuromechanics of human movement. And specifically, we are interested in better understanding how the different systems involved in human movement actually work together and how are they integrated. So here's the central nervous system, of course, the spine and the brain, the musculoskeletal system to execute movement, but also the sensory systems that basically provide sensory feedback information to control such movement. And in terms of the different domains, we look at a couple of different domains here. First of all, postural control, also from my earlier days in Toronto. So here, in terms of a better fundamental understanding of how we control posture, but also in terms of developing better quantitative assessments to really see when there are problems with a posture. Also more lab-based assessments, but also wearable assessments. Another domain we're looking at is gait, and specifically with the focus on gait stability during perturbations. As you will see moving forward, we have a nice tool here in Edmonton, the Karen. I'm sure many of you have heard of it. So we take advantage of that tool to perturb people during gait to come up with better assessments for gait stability, but of course at the same time also enhance fundamental knowledge. Since my time here in Edmonton, I've also looked at the upper limb with some collaborators here, and specifically focusing on combining kinematics, upper limb kinematics, with eye tracking. And then finally, also interested in more psychophysical experiments, and that's more focused on the sensory systems to see, how do we modulate sensory motor processing times, and what are factors in signal processing sensory motor times. So with this in mind, a couple of specific research fields that we're working on. First of all, as I mentioned, to identify or more mechanistic understanding of postural control and movement in general, but also to develop more innovative and more quantitative assessments when there's a problem with movement, and here focus on lower body foot deformities in kids with cerebral palsy, for example, the upper limb, as I mentioned, with kinematics and eye tracking, and also in collaboration with Dr. Rouhani, wearable sensors for postural control. And finally, looking at the rehab domain, either developing or taking advantage of tools that will allow us to improve therapy and rehab in a clinical setting. We have a few different facilities that we take advantage of. One here at the Glen Rose Rehabilitation Hospital, a standard gait lab with the typical tools that you see in a gait lab, and that's also where we see a lot of the clinical or where we perform a lot of the clinical studies with kids primarily, but also with other populations. Then also at the Glen Rose Rehab Hospital, the CAREN, the computer-assisted rehabilitation environment. The key aspect here is really that perturbation platform with 6 degrees of freedom and that virtual surround that allows us to basically immerse individuals in that virtual reality. And then, of course, at the university, our lab, which allows us to do a lot of different research projects, but a lot of work focused on non-disabled individuals. Now, this lab is co-directed by Dr. Hossein Rouhani and myself. So since we have a good overlap in research projects, it makes sense to combine our efforts in terms of this lab space. And here also lots of different tools that we can take advantage of. So with this in mind, couple of further comments here on my group. My group's always around 10, just below 10 individuals. I like to keep it at that size, but trainees come from a different range of backgrounds, a lot of engineering students, but also backgrounds of rehab medicine, kinesiology, and also neuroscience. We've secured research funding from different funding organizations, of course. Couple of collaborations here in town, and I will just go quickly through this here with the upper limb, with the Blink Lab, rehab robotics, more focused on back pain with Dr. Greg Kawchuk, ACE Lab, Craig Chapman, more on the neuroscience side of things. Some concussion testing with the Biomedical Instrumentation Lab with Dr. Chris Dennison, and the Smart Network, as Babak already mentioned, and the core group, which really focuses more on the orthopedic side of things. All right, with this, I hope you have a bit of a kind of background of the work we do. I want to focus more on trunk stability in this talk. And trunk stability, as you may know or not know, is really a big problem in a lot of different individuals. It can, first of all, result in seated imbalance in those individuals, and causes can be neuromuscular impairment, such as stroke, for example, but also spinal cord injury. Aging, of course, could be also a reason for seated imbalance and trunk instability. And this type of seated imbalance can actually result in problems such as an increased risk of falling, but also loss of functional independence and secondary complications, such as kyphosis, pressure sores, but also problems with respiratory function. So in this context, I'm going to talk about 3 studies. As I mentioned earlier, I hope you'll be interested in at least one of these 3, hopefully in all 3 of them. First of all, we're looking at a more fundamental study to identify and hopefully later assess mechanistically human trunk stability. Then I'm going to move on to look at a new development to train human trunk stability in different populations. And that's our instrumented wobble board. And then as a last part, more clinical focus, a new means of restoring human trunk stability and some initial data where we use non-invasive spine stimulation and the effect on trunk stability following spinal cord injury. So with this in mind, let's focus on that first one, and keep in mind that's more of a fundamental study. And the goal here is to really obtain a mechanistic understanding of how we control trunk stability. A bit of background here. Now this control system, if you think about sitting, for example, many of us doing this right now, requires some feedback control. And remember, I talked about the sensory systems, the musculoskeletal system, and also the central nervous system. So they're all tied together, and we will see later how. So when we want to identify such feedback control, we have different ways of doing that. We can use descriptive measures. And these descriptive measures have been applied during quasi-static tasks, such as upright standing and upright sitting, but also during voluntary motion, if you think about reaching, for example. And these descriptive measures are quite beneficial. However, they don't provide a mechanistic understanding of the underlying control mechanism. So in parallel to these descriptive measures, we can see system identification, which allows us, in the best case scenario, to really quantify the different aspects of that control system. And we'll see in a minute how this may present. There are different approaches. The direct approach. Now, the direct approach is not applicable to this scenario of trunk stability because it's a closed loop control system, and the direct approach should not be applied to such closed loop control systems for reasons related to noise that is present in such system, which leaves us with 2 different methods, which is the indirect approach and the joint input-output approach. And they are both acceptable methods. For the indirect approach, we require prior knowledge of the dynamics of the system. So there are some assumptions involved. So we chose to use the joint input-output approach, which allows us to identify the different aspects of this control system. So here, let's take a step back and look at postural control during sitting. And there are different aspects involved. So there's feed-forward control. And what this basically implies is that we have some level of internal models in our brain that allow us to execute a motor plan that has been developed through previous learning and experience. So if you think about a child starting to walk, that child's falling over a lot, but through that falling, it actually learns to walk, and the brain is able to generate these internal models and execute them when they're required. So if you think about upright sitting, for example, and you're being perturbed, for example, sitting on a bus that suddenly stops, then we can execute those internal models. However, they are not tuned based on sensory feedback. So in addition to this feed-forward control, we have feedback control. And there are 2 aspects involved in this. Passive elements based on the tissue stiffness and damping of the trunk primarily, and also intra-abdominal pressure that is present during sitting. So these are passive components that are more mechanistically driven by mechanical aspects, and there are also no time delays involved. And then there are active control mechanisms that actually require information from the sensory systems. That information is being sent to the brain. The brain integrates that information to send a motor plan to the muscles. That may be happening while the feed-forward control is active, and activate relevant muscles that will help with stabilizing the body. So what we're trying to do here is to identify the dynamics of some of these elements, and the more the better. And we're currently focusing on that feedback control, especially the active and the passive control. So if we now model this system, the feedback control model, now keep in mind, we're now excluding the feed-forward control. We can look at different blocks here. And again, yes, I have my engineering background, so I like these blocks, but of course, you could visualize this in a different way as well. So we have the body dynamics that we're trying to stabilize. We often call this the plant. Input is the torque, and the output is the body angle. We compare this body angle to our desired position, which we call the set point. But in order to do this, we got to measure the output via our sensory systems, which involves the sensory dynamics and a sensory motor time delay. Now, this sensory motor time delay happens at different points in this closed loop system. But we're just modeling it here with one single block. Once we compare our actual angle to that set point, which is our desired position, we engage our neural controller, and you can see there's that image of the brain integrating that sensory information to then activate the muscles. Again, that requires a time delay, and generate a torque that will stabilize the plant, which is the body, right? Now that's the active loop. In addition, remember, there's that passive control that helps with that torque, stabilizing the body. There are no time delays in this loop. And we're specifically identifying aspects such as stiffness and damping that contribute to this mechanical control. So in this context, what we want to identify are these blocks here, and specifically the dynamics of the neural controller, of the muscular system, and the mechanical dynamics, as well as the sensory motor time delay. Now, if you could look back, you can also see there is a block with the sensory dynamics. Now, that would require perturbing your visual surround, for example, or your vestibular system, and we're currently working on that. Right now, we're focusing on these 4 blocks, which, as you will see, require some mechanical perturbations. So here specifically, what we did is we invited healthy, non-disabled participants to participate in the study, and specifically individuals who had no history of neurological or musculoskeletal impairments. And we recorded different sets of data, specifically the motion of the upper body, but also muscle activity of the different muscles of the trunk, and also some of the leg muscles. And we also looked at the ground reaction forces, of the sitting surface where the individual was sitting. So quite involved here. And keep in mind, I talked about these sensory perturbations. In order to actually identify the system using this input-output approach, we need to apply external perturbations that are well known. So because of that, we're using the Karen system for this project, where we're able to provide these perturbations while an individual is sitting on that platform. So the protocol here was as follows. First, of course, there was a health screening involved. We placed our electrodes. We obtained some baseline EMG and MVCs that we needed for normalization, placed the markers, of course, and performed some anatomical calibration for the kinematic recordings. And then we had 2 different tasks, pretty straightforward: quiet sitting as a benchmark, just 1 trial for 2 minutes, and then perturbed sitting as well. And here we had 3 different trials. Now, these are pretty long trials, and these are the trials where we apply these slow, continuous, and pseudo-random perturbations. And you will see an example of those perturbations in a minute. So a couple of more comments on those measurements. So in terms of the kinematics, these are all the different markers that we use. This was actually quite involved project in terms of the preparation and data acquisition and then later processing. But from these markers, we were then able to obtain body sway. And specifically, we looked at a single segment trunk model at this stage. And then, of course, with the data set we have, we can also expand it to multi-segment studies in the future. So from the markers, we obtain the body sway, which we will need in our system identification. We also obtained the muscle activity of these different muscles, mostly the thoracic, so the abdominal muscles, and then on the trunk, on the back side, as well the back muscles, and specifically here the erector spinae at different levels. And our goal was here to obtain from all these different measurements one single EMG measurement with specific weights for each muscle that will basically be representative of the muscle activity for the entire trunk. And we'll talk a little bit more about this when we look at some of the results. So this is the output here. So of course, we have many EMG signals, but then we want to obtain a single time series, which basically represents a weighted EMG signal. With our measurements from the force plate and also our kinematics, we can also estimate the joint moments, and specifically here for that single segment model of the upper body, we need to obtain one particular joint moment. And here, keep in mind, we're only looking at the anterior posterior body fluctuation. So the goal here was to identify the control system in the anterior posterior direction. So with this in mind, we have a few different measurements, and we have this external torque. So here I mark it as D external, and that's basically that surface platform that we perturb continuously to perturb the body during these sitting trials. And by doing so, we're able to identify the closed loop control system because we have a very controlled measure of the noise that is in the system. We want to measure the weighted EMG. Remember, that's kind of a combination of the different EMG signals that we obtain. We measure the torque. Now, measuring meaning the force plate signals and the kinematics will allow us to estimate the torque. And we're measuring the body sway angle, again, based on the motion capture markers. So with these measurements and with the external torque, we can actually identify the different blocks in the system. And for this purpose, I'm not going to go into the details here. We use the cross-spectral density between two signals. So for example, at the top here, you see the cross-spectral density between the external perturbation and the torque. And then in the denominator between the external perturbation and the body sway. And this will allow us, for example, to identify the control system for the passive and active system together. And we can do the same thing with the EMG and the body sway angle. And that will allow us to identify the active control system and the time delay. And so with the different equations, the third one here as well, we can actually isolate the different blocks to mechanistically identify the underlying dynamics. Once we do this, we can basically perform two steps. The first step we call a non-parametric estimate, and I'll show some plots of these. So we don't have specific values associated with those plots. And then we can go one step further to identify the parametric estimates. And this involves some further optimization. We'll use different tools to identify the different controller gains, for example, for the neural controller, and then evaluate how good that fit actually is. So let's take a look at some of the results here. First of all, the EMG weights. Remember, we combined the different EMG signals into one EMG signal using different weights. These are the different muscles that we're looking at. And the only thing that we assigned was the sign, positive or negative, for the abdominal muscles versus the trunk muscles, and the same for the leg muscles. And then we optimized the coherence between this weighted EMG signal and the perturbation signal. So when we saw the highest level of agreement, so to speak, then we had our optimized weights. So now these are the results across all participants. And yeah, we had a very good fit in terms of the weights, and then also in terms of the value of the coherence between that weighted EMG signal and the perturbation signal. Let's take a look at these time series signals. The first signal here is our perturbation. So that gives you a sense of how this platform was moving. Now, this is a surface perturbation in the anterior direction, anterior posterior direction, and we translated this perturbation, which is a displacement, into a torque. The second plot shows you the body sway. Remember, we identified that through the motion capture markers. The third one, our weighted EMG signal. And then the last one, our estimated torque, again, from the motion capture data as well as the force plate data. And you can see, obviously, it's not surprising, there's a relationship between that perturbation and the body sway, but also the torque that we apply during that moment. And I'm just picking one particular time here. And same for the EMG as well. So in terms of, yes, I see there's a question, I believe. I think the questions will be answered through a question and answer box here. But if you can. Okay, I don't see anything in the question and answer window. So I'll just continue for now. And hopefully at the end, there'll be time for questions. I am monitoring this window. So far, I don't see any questions in that window. So I'll keep going for now. Okay, perfect. So let me just go back here. There we go. So now we looked at the time series data. Let's look at the non-parametric estimates. Now these are frequency plots, basically capturing the dynamics of the different control systems. Now, as you can see, we still have the overall active control system on the left-hand side. And on the right-hand side, we have the combination of the active and passive control system. So here we're not capturing the dynamics of the single blocks, but of the overall system, first for the active system and then for the active passive system. And again, I'm not going to go through this in detail, but what we see here across participants is that we have a pretty good fit in terms of the variability across participants. So the middle line each time is the mean across participants, and then we have the dashed lines, which shows us the variability. And this is actually a big challenge in these system identification studies to make sure the data converge and that you have a good fit across participants. So what do these plots represent? They basically present kind of a black box, as you can see here at the bottom, between the input and the output. So really capturing the dynamics of these two systems. If we continue, we can now model these plots, and these are actually different plots on this slide, where we're now trying to model these dynamics according to the experimental data. So one line gives us the experimental version, the dashed line in this case, and the other line gives us the modeled version. And once we have a good fit, as we have here, we can actually identify the different parameters of the different control blocks as we've seen earlier. Remember, we looked at the passive controller, the active controller, the muscular dynamics, and the sensory motor time delay. So here on the bottom, just a couple of numbers in terms of the fitting. And these numbers tell us that we actually obtained really good fits between the experimental data and the model data. So what we found here, and you can see these equations here at the bottom, and again, no need to understand all the details, but there are different control aspects that are involved. For example, for the active control, what we see here is that we have a proportional derivative controller that is combined with acceleration feedback to really generate that torque to stabilize the body. Now, PDA, that means we use sensory position information, sensory velocity information of the body sway, and acceleration as well. Now, the question is, and there are different studies on this. How can we actually measure acceleration with our sensory systems? That's still an open debate, but there is some evidence that shows we can actually measure acceleration directly. Also, if we look at the active-passive control, now keep in mind that's a combination, we see that the passive controller actually represents a PD controller. So on the mechanical side of things, we're looking at position and velocity as the controller gains that stabilize our body. And then, of course, we look at the muscle dynamics, and we found that we see a second-order transfer function for generating the force and then the torque, which agrees with previous literature. So I see there is a question here. Oh, just a test. Perfect. So the test works. So if there are any questions, then please post them in that window for the questions and answers. Thank you. All right. So what does this mean now? So first of all, okay, oh, I got it. There we go. Here I'm presenting a table that shows some of the parameters that we selected prior to the study, such as the moment of inertia. Remember, we have a model for the upper body. We also look at the length based on each individual that participated, the length from the joint to the center of mass, and of course also the mass of the upper body. So you see here mean values and the standard deviations for the participants. So those are based on the experimental data of the specific participants. And then with our system identification, we identified the different gains and different parameters of our control system. First of all, the active stiffness. So remember, that's the active controller, and we have a proportional controller, so that's based on position. Then the damping, that's based on the velocity of the movement, and then the acceleration. We identify specific numbers, quantities here, also with a certain level of variability. Then we identified the sensory motor time delay, which was about 40 milliseconds, which makes sense if you compare it to previous literature. And then a couple of constants for the muscle dynamics, and of course our passive controller as well, the position controller, KP, and the derivative controller, the velocity controller gain, dP. So take-home message here is what we found is a specific sensory motor time delay that's involved in that closed-loop control system. We found a PDA controller for the active control, so position, velocity, and acceleration is being used for the control. And on the mechanical side of things, the passive controller, we have position and velocity control. So why is this important? Well, first of all, we can use this information to better understand how we control sitting posture during perturbations. So here, what we learned is that the brain utilizes the body's displacement, velocity, and acceleration in this task. And for the mechanical controller, we're looking at the displacement and velocity information only. Keep in mind that the active control loop is affected by a time delay, and that's about 40 milliseconds. And with this identification, we can also use this information as a benchmark if we test individuals with impairments. So for example, now this protocol, of course, is heavily involved, but we're working on a simplified version. We'll talk about that one slide down. If we can do this with clinical populations, we can see, hey, it seems there's a strong deviation in the muscular dynamics. So there must be some challenge with the musculoskeletal activation, or maybe with muscle strength. Or we can see some problem with the time delay, that the time delay has significantly increased. Then we can target the signal processing time rather than the muscular activity. So the hope here is that we can use this tool set and these results as a benchmark for quantitatively assessing impairments and really identify underlying mechanistic causes. So quick summary here. What we need to do still is we need to assess the reliability of the identified parameters with a larger set of participants. Of course, we may also need to look at the medial lateral direction. We need to reliably estimate muscular dynamics, the sensory dynamics. Remember, we did not identify the sensory dynamics, and the human body dynamics, where we assumed a specific model. And in terms of the clinical context, we can compare these parameters, as I said, to those obtained in different populations that are affected by seated imbalance. I mentioned the medial lateral body sway direction. We need to look at that as well. And we're also looking at miniaturizing the system to make sure we don't need the system such as the Karen system to actually be able to assess individuals with seated imbalance in a more practical, feasible manner. And finally, some of these results may also be used for the development of assistive technology, for example, after spinal cord injury, where we can use some of these aspects of closed loop control to drive our stimulation in closed loop control scenarios. So far, so good. So that's the first study. And as I said, more mechanistically driven, trying to obtain a fundamental understanding, but also with the overall goal in the future of clinical translation. But more work is needed on that one. In the second study, for those who like design, this may be something for you. We're looking at a novel technique to train human trunk stability in those individuals who are affected by trunk instability or sitting imbalance. In the past, including myself, we've used these descriptive measures to assess balance, for example, during quiet sitting, but also during quiet standing. Here, for example, looking at some force plate signals, center of pressure fluctuations. Again, don't obtain really a mechanistic understanding, but you can use them to assess individuals' performance. Now, what we've learned over the last years or decade is we really want to perturb individuals to see how they respond to such a challenge and really capture the dynamics that are involved in the restoration of stability. And we've done this, for example, in that previous study. And we have seen this, that we can identify the system using these perturbations. But what about assessment? Because with this system identification, we're not there yet where we can use it for clinical assessment. Now, previous efforts have used different ways of training balance. And so we're also looking at developing a device that can not only assess sitting imbalance and sitting stability, and ideally quantitatively, but also train sitting stability and sitting balance. So here, what other people have done is they used sensory feedback, tactile feedback, to really promote the learning involved in this task. And we want to basically tap into this with our device that can be used for training and assessing seated stability and seated instability. So the goals here are to develop a portable device for perturbing seated posture. And such a device includes onboard instrumentation that can accurately quantify postural proficiency, and that can also deliver vibrotactile feedback to the user. So this should be a self-contained device that's also quite mobile. And the second objective was to evaluate the feasibility of using this device to assess and train sensory motor function, specifically for sitting. And in this case, by assessing and training a sample of non-disabled volunteers under experimental conditions. So what's this device? It's basically a wobble board that we've designed that includes different bases of imbalance. So you see these curvatures here under 5, so you can introduce different levels of instability. It can measure the kinematics of the wobble board, but it can also provide vibrotactile feedback to the seated user, and also footrest if you want to perform your study or your assessment with such footrest in place. Couple of key comments here. It provides modular instability. As you can see, the different bases. It perturbs individuals continuously in all horizontal directions. So it's not just anterior posterior direction, for example, or medial lateral. It's all directions. It provides that continuous instability as mentioned, and it's portable and accessible. So what about inside? Inside we have an IMU, which measures, with some processing involved, our angles. We're looking at the vibrotactile feedback elements that are arranged in an octagon, so we can actually activate them based on those kinematics in different ways, if we like. We have a controller, of course, a microprocessor that integrates the kinematic measurements, makes sense of them, and then provides that control to the vibrotactile feedback or the vibrotactile elements. And the first one, as mentioned, quantifies postural proficiency, and we can use previous measures to really quantify that postural proficiency. And we're also looking at real-time vibrotactile feedback to see whether it actually has an effect on performance within a session, but also, through learning, and potentially take that vibrotactile feedback away as well. So we tested this technology in a smaller group of participants. We had a few different conditions. The base difficulty, we looked at 2 different bases: eye condition, eyes open, eyes closed, and vibrotactile feedback on and off. And then basically looked at some of those measures that previous studies have looked at in terms of the stability of the system. Again, these are more behavioral measures. They don't really identify the underlying causes as such as system identification would do. So what we found here is that the base had an effect on some of those measures, specifically the frequency dispersion. With easier base, the frequency dispersion was larger. With the different eye conditions, we also had a difference for the frequency dispersion. Same thing for eyes open, a larger frequency dispersion. And then with the vibration, we also saw different significances for 2 other measures. So larger RMS when we had no vibration, and larger centroidal frequency, basically means of the average frequency involved when we do have the vibration on. So it seems that there are some measures that can detect mechanical stability and differences, independence of that base of support, but also independence of the eye condition. And we also found that the sensory feedback technique can improve postural proficiency as well. So that's just a small first study in individuals who had no impairments with trunk stability. What we want to do next is extend this study with a training protocol, but also apply this technique to individuals who've suffered under a stroke. So a couple of take-home messages here, and I got to move a bit quicker as I see the time's ticking here. First of all, this device combines elements of other biomedical devices into one portable, accessible device, elicits instability in all directions, and this of modular degree of instability, and it's instrumented to meet the specific goals of clinical assessment and training paradigms. In terms of the first experimental validation, we've assessed and trained, well, I wouldn't say trained, but we've looked at the effect of the tactile feedback on non-disabled individuals. We can see that the assessment technique can actually distinguish eye conditions and instability levels. And we saw that the vibrotactile feedback can facilitate improved performance of dynamic sitting in that particular moment. Now, keep in mind, we had multiple trials, so we also looked at the learning effect there. So with that, keep in mind, we're using this right now for 2 studies. First study is about a clinical population, seeing whether it's actually useful in the clinical context with stroke survivors. And the other one is a larger sample of individuals with a training paradigm as well. Let me quickly look here at some of the questions. So there's a question, if we look at the first study about the anterior-posterior direction and the medial-lateral direction. The question is whether, let me just, right. So this is a good point. So in the second study, I'm looking at the multidirectional approach, basically.
Albert, this is Babak. For the recording that we'll post, can you repeat the questions?
Yes, for sure. Okay, the first question here is, do you think your model will change drastically when you look at mediolateral perturbations? Or in other words, is there a reason why this wasn't included in these initial trials? So the reason why we only looked at the anterior-posterior direction was that the protocol itself is quite involved. So we first wanted to see whether this approach is feasible and whether we can actually have the data converge. Remember those non-parametric plots that we saw. And then moving forward, we would also look at the mediolateral direction. So the question is certainly justified. Obviously, there's control in both directions, and that control, which relates to the second question, which I'll repeat in a minute, that control may not be disconnected from each other. So there may be an overall control system that's controlling, all directions, as we maybe see here with the wobble board. But as our first system identification study with sitting, we only focused on the AP direction to see whether that's actually feasible. Moving forward, we are going to look at the mediolateral direction as well. And then the question also is whether there's a way to combine those two directions, maybe in form of a multi-directional perturbation. Which relates to that second question as well. You have just shown AP modeling. You can do ML, but when sitting balance is multidirectional, as you're demonstrating now with the wobble board, yes, I agree. Can you also, I believe I'm paraphrasing here, can you also use a multidirectional perturbation for the first study? And yeah, so as I said, that would be the goal. For now, we're looking at the AP direction. ML, I would still do separately in the first case, and then probably in the same experimental setup, combine AP and ML as well as additional trials to see whether we can come up with a common control system and how that would agree with what we've identified for the AP and the ML directions. I hope that answers the questions. If not, please feel free to follow up, and then later on I can take a look again. Thanks so much for these questions.
Albert, this is Balak again. There are also two questions in the chat box. I don't know if you can see them. If not, I can read them.
I don't see a chat box here, only the Q&A.
Okay, I can read them. There are two questions there. One is about study 1. It says, is 40 millisecond a total time delay? How does this number compare to physiologically measured time delays?
Right. So in terms of the transmission time, I would say makes sense. Transmission time delay for upright standing has been shown to be around 80 to 100 milliseconds just for transmission. So if we look at the distance from the sensory systems for the trunk to the brain, and then again back to the muscles, about half of that would make sense. Now the question is, how much time does it take to integrate that information in the brain? And there are different views on that. So if we just treat it as a transmission time, I think it makes sense compared to previous studies. Also keep in mind the muscular dynamics, they have their own time delays involved in those dynamics. So the identified sensory motor time delay of about 40 milliseconds does not include the delay due to torque generation.
And there's a second question that says, in study 2, how did you provide vibrotactile feedback before the perturbation or during?
Yes.
And does it lead to anticipatory adjustments or an improved sensory during the perturbation?
Yeah, that's an excellent question. So we had 8 tactors, and we grouped them always into 3 for each direction. So for forward movement, we had 3 active, backward 3 left and right. And so how were they controlled? It was based on a paradigm that combined the tilt with the tilt's velocity. And we optimized the the occurrence of the stimulation based on previous studies that's shown if you have too much stimulation, it's not going to be beneficial. And of course, if you have not enough stimulation during a trial, it's also not going to be beneficial. In some cases, it actually can be, more detrimental in terms of the stability. So following those studies, we were in a range of 30 to 50% of activation. But how were they activated? With those 4 different directions and based on position and velocity. And that's a stimulation paradigm that can easily be changed for a particular context. Perfect. Any other questions? All right, so I'm going to move forward with that third study. And so remember, I talked about more fundamental work at the beginning, mechanistically driven, and then more development of a device for assessment and training. And so in this third study, we're looking at a technique, stimulation in particular, to see whether it can be used to restore human trunk stability, or at least facilitate human trunk stability. And in this particular case, we're looking at non-invasive stimulation of the spine. So here, as mentioned earlier, also individuals with spinal cord injury are affected by trunk instability. And so those impairments are common. And so how can we help those individuals? And the question is, can we use stimulation that has been used for enhancing standing balance, but also gait? Can that be used to enhance trunk stability as well? And specifically, we're seeing whether electrical neuromodulation of the spinal networks can actually improve the control of the movements, and here specifically of the trunk. So this is derived of previous work and applied to the trunk, and a purely experimental study. So objective here was to investigate whether such non-invasive transcutaneous electrical stimulation, and specifically focusing on the lumbosacral enlargement, can improve trunk control and stability. Now we can talk about that location because you may think, well, that's probably more targeted for the lower limbs, and so why would that help with the trunk? So we'll take a look at that as well. So what we had here is we had 8 participants with spinal cord injury, and there were a few tasks involved. They had to sit quietly, and they had to also lean into different directions, actually in 8 different directions, and they also had to rapidly move one of their arms up, which requires some trunk stability as well. We applied the stimulation to 2 different sites, T11, 12, at the thoracic level, and then L1 and 2. And all the stimulation was provided at the submotor threshold. What measurements did we take? We looked at 3D kinematics again, the center of pressure, and EMG, so very similar to the first study as well. Just keep in mind, these are different tasks here. There are no perturbations involved except that, the self-induced perturbations, the leaning and the raising of the arm. On the right-hand side here, you can just see the different protocol steps that we've applied. So not much time left. So let's take a look at some of these results here. Remember the quiet sitting, and I'm just looking at the comparison here between no stimulation and stimulation. Top plot is the center of pressure fluctuation, and the color shows you, the frequency of currents of a particular location. So you can see with the stimulation, it's much tighter. The bottom, we see the muscle activity, looking at 2 specific muscles. We can see there's more activity for the T7 level, so that's the erector spinae at T7. Furthermore, if we now look at the group results on the left-hand side, the center of pressure, we saw a significant difference here in the COP fluctuation, and then also significant differences for the EMG levels for some of the muscles, especially for the erector spinae. Now, interestingly, you see those differences between T7 and L3. So that may also that may also relate to some of the kinematic results that we see on this page here. We saw that people were able to sit more upright with the stimulation on. So that's the red curve here. And so that's measured with the trunk curvature, which was reduced. And the trunk angle was actually increased, which goes hand in hand with that change in trunk curvature. Moving on to the leaning, remember 8 different directions. We saw a similar result for the center of pressure fluctuation. So individuals were actually able to lean further. Now, again, this is one participant here on the right-hand side with the stimulation on. So now we expand the plot because they're able to lean further with the stimulation. And for the body kinematics and the EMG, very similar results compared to the quiet sitting, less curvature, and also more activity of the different muscles as well. So yeah, I'll go through this quickly. I wanted to provide more details, but I'm running out of time here. Last plot here, remember the arm raise. We see again, there's more activity in the muscles. We have the anterior deltoid, rectus femoris, rectus abdominis, and then again, rectus spinae at T7. And also the displacement of the arm was increased, and also the displacement actually of the body sitting on that force plate during the stimulation. So I'll just finish up quickly. Hopefully there'll be still some time for some questions. So what we saw is that the stimulation at that location improved the self-governing control of upright sitting. And that improvement may be reflective of changes in the spinal and supraspinal networks. And so these are just basically initial results, kind of a pilot study. So we want to see whether we can actually use them and maybe optimize the location of the stimulation. Now that's of course tricky in terms of the heart location, but also in terms of having targeted the right area of the spine. So ideally, there's some mechanistic study that looks at different locations and the optimization of the output. So yeah, of course, in the end, we also need to see whether these results translate into more function and independence, whether as an assistive device or whether in terms of providing some kind of training protocol using stimulation, as has been done with other tasks with stimulation. So with that, I'm 1 minute before 11 my time. So if there are any questions, please let me know. I'll check out the question window as well. And of course, thanks to all the collaborators and the students working on this, and of course, the funding organizations. Thank you very much.
Perfect timing. There are a couple of questions in the Q&A, and there's also one in the chat box.
Perfect. So I'll start with the Q&A one. How do you differentiate neurological impact of the stimulation from the muscle contraction caused by the stimulation? Can you decouple these? If yes, how did you do that? Yeah, that's an excellent question. So we did monitor, and that was one of the reasons why we had this location of the stimulation. We did monitor the artifacts of the stimulation in the EMGs, and we had hardly any artifacts. So our conclusion was that mostly neurologically driven. However, more evidence is needed on this. So currently what we're actually looking at is using invasive stimulation to, and we have an opportunity where the electrodes are already implanted, and we look at different locations to see whether such results would actually agree for the implanted stimulation compared to the transcutaneous stimulation, to see whether we would obtain similar behavior in terms of the sitting kinematics, force plate, and so on. So two-part answer here. Artifacts were very low, if even present, for the muscles. And we need to follow up looking at different locations where we just stimulate the spinal aspects, and therefore we would avoid the muscular activation as well. And then chat. Oh, there you go. I found the chat.
It's actually the same question. So the questions in there are two more in the Q&A.
Two more in the Q&A. Okay. Oh yeah, got to scroll down there. I have two questions on study one. As far as I remember, for the typical joint input-output method, we need to know the perturbation. or we need two known perturbations, sorry, while you used one mechanical perturbation. Can you please comment on that? Yes, depending on which blocks you want to identify, you need two perturbations. And so what we did, we also perturbed the sensory systems, and specifically the visual system with the visual surround. So we do have those two perturbations, and those two perturbations allow us to identify all the different dynamics of the closed loop system. Keep in mind, we were not able to identify the sensory dynamics. And so that would be required for that. That is exactly true. The global average CSD is often used to identify a global system, while I guess you identify system for each participant. Were you able to identify the system for everyone with good fitting? So yes, so we did apply the CSD for each individual separately, and doing so, we were able to identify it with that fit. And if you look at the overall plots of the non-parametric estimates, you also saw that the variability across participants was quite low. And then last question here, do you measure respiration at the same time? And does the level of lesion or degree of paralysis influence postural control? That's an excellent question for the third study. We did not measure respiration, but that's an excellent idea, and how that may be influenced. And yes, in terms of the level or degree of injury, we certainly saw differences across the participants. So if you look back at the bar plots, for example, you see some variability there. We didn't have enough participants to group them to see whether there are consistent trends. So, but that variability existed, yes. I believe that was the last one in this window. And the chat, I believe, was it too. Perfect. Any other final questions? And my apologies for going over time here, but it's been fun and a pleasure. So thanks for joining and listening.
And on behalf of myself, the Institute, and everyone in the audience, I also thank you. I hope you can join us in person after the pandemic is over. And everyone, please join me in thanking virtually our speaker.
Thanks very much, Babak, and all the best to everyone, and please stay safe.
Thank you. Bye.
Bye-bye.